I wanted to talk to you about rotational impulse. We have discussed torque and the second law of motion for rotation already. And just like impulse of a force, you can have an impulse of a torque. Okay, so this is basically what it's saying is what's the impulse of a torque. So if you so this stands for impulse of a torque. So if you remember impulse of a force, so impulse of a force is this. Say force is changing in magnitude, it's not changing in direction. So we're just going to look at an example where constant direction. Okay, so during the time, so we're just going to look at the magnitude. So if you look at the magnitude of the force versus time, if you look, you can get some kind of plot here, depending on the system. So if you're applying a force for a certain time, say if this was some f0, let's call it, and you apply it for some time t, and this was constant, and then it was 0 after that, then the area, this area, it gives us the magnitude of the impulse. So this gives the magnitude of the impulse. Of course, here is just f0 times t. You can have quite complicated behavior. For instance, when you hit a ball with a bat, it might be before the bat was in contact is 0, but when it's in contact, it can rise very quickly, and then when the ball is leaving, it can fall very quickly to 0, and ball is no longer in contact. So you can see if I know the shape, this depending on what function it is, I'm looking for this area. So this also give me the magnitude of the impulse. And sometimes this kind of situation we kind of approximate with the area of a triangle with something over here. So if this was 0 and this is t, so this is base is t and height is f0, so here it will be f0 t over 2. Here f0 t, the area would be f0 t, and so we call impulse letter J and impulse letter J here. So this is for the case where the direction is constant. If the direction is not constant, we need to work with components and things like okay, so we can work the same kind of area under a curve, but we'll work for the x component of the force, the y component of the force. X component of the force, if we look at the area under the curve, is going to give me x component of the impulse. Y component of the force will give me the y component impulse, and so on and so forth. And then we can put them together. Impulse as a vector, we can put the x and y components, the impulse, together, magnitude of the impulse and the direction of the impulse. So that's a review of what the impulse of a force is. It's similar here. Often when we try to rotate a wheel, so you take a bicycle wheel and suppose you have axle, hold the axle, you're going to hit that side. You can hit the side to get it rotated, right? And so your hand is like in very short amount of time in contact with the wheel, right? The rim of the wheel. So so here it is. So I have something I'm trying to rotate, and I put a force on it that actually comes in contact and leaves. So if I look at the force duration, it kind of comes in here, and it's like that. Well, if you pick any, say, time t1 here, okay, so at that time the force magnitude is, say, F1, and you have radius for, if you do the the distance to the force and multiply it, get a torque. So this will give me R, which is R here for this, say, wheel, R times F1 will be the torque at that instant. So if I plot in this particular example, because R remains same, so if this was, say, F0, what you're going to get is torque in this of this force with time will be almost like the same curve, okay, except that it will go all the way to R F0. At T1 is going to be, the torque will be R F1. When you look at the area under this, that gives what is called rotational impulse. Impulse of this, in this situation. Of course, you can have other types of forces. Maybe you have maybe you hung a wheel and you have a block that goes around it, okay, but then you only have maybe this much thread. So what will happen, the thread will unwound, and this tension is some kind of constant. That's the force. So if you look at the tension force of tension with T, it's constant till all of this unwounds, right? So that's the time that it has, the last bit just fell off. But this is force picture. Here, if you look at how much torque by so this is some Ft which is constant. Tau of Ft is almost the same thing as except that I have R times Ft and goes to 10. So this area is again very similar, because the example I'm presenting is R is same in all these cases. So just multiplication of that makes sense. So what is rotational impulse? For rotational impulse, in general, I am going to have rotational impulse. If I erase this special examples, we'll have, if I take a force and I plot its torque versus time. So if I take a force and I figure out torque of some force, I plot versus time, and whatever I get, when I add up these areas, maybe I get, the force just keeps becoming bigger and smaller, so to say, So this is the torque. It's kind of complicated. So when I add up area, total area, that gives me rotational impulse. If I was applying a torque this way and then I change my mind and apply the torque the other way. So for instance, in the wheel, suppose you doing that way and then say it's going too fast, I'm just going to do it that way, and you add up all of that. So if this was plus, then this will have to have minus, right? So if the wheel is, if this one rotates the wheel this way, this one will rotate the other way, so this impulse will slow it down and this will speed it up. So you can see that I would have to be very careful about plus and minus, whether it's a clockwise or counterclockwise sense. So when we work with this guy clockwise or counterclockwise, the rotational impulse will be clockwise or counterclockwise. And clockwise rotational impulses will add together, and counterclockwise rotational impulses will add together. And they will, if I have two of those guys in opposite direction, they will subtract, and the bigger one will win. All right, so we can do some examples of rotational impulse later.